Okay, so we want to talk about problem 4 here. And what I want to do is review how we normally build lines and give you a hint as to how to handle a problem like this. So yeah, let's switch over to the other mode here. Alright. Boy, something is seriously sucking up CPU on this machine. Alright, so let's pretend we got a point P and a point Q, and we want the line that goes through them. Typically what we would do is we would convert P to a vector, and we would just write okay, I know what happened there. I'll tell you exactly what happened there once it comes back up. So whenever I switch modes on this thing, I get this little box that says, "Are you happy with the new settings?" and a countdown. And if I don't say OK within a certain period of time, say 15 seconds, it goes back. I don't know why it has to ask me that every time, but it does. Okay. So typically when we parameterize this thing, we vectorize, or we turn the point P into a vector, and then we just take a scalar T times the displacement vector PQ. And one of the things that this process gives us is it gives us a parameterization where L of 0 is what? P, and L of 1, perhaps a little subtler, is Q. Remember how we form this thing? It's just Q minus P, right? And so when T is 1, we have P plus Q minus P, which is Q. So if you're building your parameterization like this, come back and look at the web work problem. If you're building your parameterization like this, you automatically have this condition, right? The problem is this condition. We want to be able to plug in 6 and get Q. Right now, we plug in what to get Q? 1. So what we have to do is we have to let the user sort of hand you a 6, and then I'm going to take the 6, and what am I going to do to it? Turn it into a 1 and shove it into the function. So how do I take a 6 and turn it into a 1? Multiply by 1/6. So that's the mysterious H function to which I alluded to in my email. So what we want is L of 6 to equal Q. So the H function in this case, the helper function, takes the 6 from the user and spits out a 1, and then you shove that into L. And so the function that you want is L of H of T. And H of 0 is 0. Does this work? Well, let's look at it a little bit here. I call this R, by the way. So R of 0 is L of H of 0. H of 0 is 0, so that's L of 0, and that's P. R of 6 is L of H of 6, which is L of 1, which is Q. And so this R behaves the way we want. So your goal is 2 pieces. You have to find a parameterization that behaves the way mine does, 0 to 1, P to Q. Then you have to find a helper function, H, that takes the inputs that WebWork is asking for and turns them into the inputs that you want, 0 and 1. Let's look a little more generally here. Let's look at the second part of this problem. Even more problematic now. In part A, we only had to tweak one of these guys. The other one was already the way it needed to be. Now in the second one, we need the 4 to turn into what? 0, and we need the 8 to turn into a 1. Okay, so we need to find a function that turns 4s into 0s and 8s into 1s. One, two, three, 4, 5, 6, 7, 8, and 1, and 0. So this is not a very... I need a little function that does that, like that right there. Okay? There are lots of functions that do this, right? The simplest one is to use a line. Can you find the line between those 2 points? H is the line between, oops, the point 1, 0 and the point 8, 1. And this is not the line, the Calc 3 line. This is the old, Algebra 2 line. Y equals mx plus b. If you can find that, that's the right H, right? Because then if the user hands me a 4, it turns into a 0. And if the user hands me an 8, it turns into a 1. And I feed that into the other guy, and that's my R. And so R of t is really just my L of H of t, where H handles this really picky user that wants 4 to go to P and 8 to go to Q. Can't just handle the 0 and the 1 thing, has to have it 4 and 8. Okay? Any questions about that, Nick?
So once you find your H of t, you just put that in where H is before the vector in the
It's function composition. So everywhere in your function you have a t, replace it with H of t. Okay, and if you look at what WebWork is expecting here, syntactically, I think it'll accept several different formats, but come on. Oh, same old networking problem here. Let's hit the X here carefully. Turn off the networking. Turn it back on. Oh, maybe it's working, who knows. That's kind of what it's looking for. For example, you can see I replaced the t with t over 6 there. Or replace the t with this. This is the equation of the line. Notice when you plug in 4, what do you get here? 0, which wipes out that whole thing, and you get this guy. And when I plug in 8, I get 1. I think you could use angle brackets here as well, and WebWork would be happy with that. I would expect that, frankly. But there are lots of different ways to write this out. Yeah, go ahead.
Yeah, I was going to say, when I submitted my answers, it accepted a pretty different format in terms of 1 vector and then 3 separate equations.
Yeah, and I'm glad that it does that. I've alluded to this before. Writing a program, writing a web interface that does what WebWork does is a pretty daunting task, because students can input answers in so many different forms, and behind the scenes there's a lot going on to say, well, is this the right answer, or is what you did the right answer, or is what he did the right answer? It's a lot of technical programming that has to go on back there, and by and large, I mean, it does a fairly good job. I'm pretty impressed with it, but it definitely can be tripped up. But it's good to know that that doesn't trip it up.
So is, in your mind, is that another acceptable way?
Absolutely, yes. And if you're writing an answer on a test, any of these are acceptable that convey to me the equation of the line. You could give me x of t, y of t, and z of t if you wanted, and I'd be happy with that. Okay. Any other questions with this assignment? All right, let's talk about differentiating space curves. So our first bit of calculus in Calc 3. Okay, differentiating space curves. I'm going to describe differentiation in both what I'll call an algebraic mode, where I'm interested in just simply how you compute the derivative. For example, if I say, what's the derivative of t squared plus t? You tell me 2t plus 1, right? That's computational, that's algebraic. We want to talk about that. How do you differentiate these space curves? And then I want to talk about the geometry of derivatives of space curves, right? What are the geometric implications of these things? And then if I get some time, we'll talk about some formulas like product rules for differentiating vector functions. We'll do a few examples, and then I'll talk briefly, very briefly, about how you integrate vector functions. And then I'll probably just let you go. All right. So differentiating space curves. We've got this definition. So we've got this function f, or r, excuse me, r of t. And it's x of t, comma, y of t, comma, z of t. And what we'd like to do is build some kind of, or develop some kind of notion of how to differentiate this thing. Now, from Calc 1, if you had a function f of x, f prime of x was the limit as delta x goes to 0, f of x plus delta x minus f of x over delta x. That should ring a bell. That's the definition of the derivative from Calc 1 on an ordinary scalar function f. What we want to do is just take this guy and lift it up to 3 dimensions. We want to lift it up to vector calc. So we're going to call r prime of x the limit, sorry, we're not going to use x, now we're going to use t. The limit as delta t goes to 0 of r t plus delta t minus r of t over delta t. And symbolically, it looks a hell of a lot like the Calc 1 version, where we've simply replaced f with r and x with t. Looks basically the same. Behind the scenes, algebraically, there's more going on in the second one than there is in the first one. In the second one, in the numerator of the difference quotient, you've got the difference of 2 vectors, as opposed to in the Calc 1 version, you've got the difference of 2 scalars. When you subtract 2 vectors, how do you do it algebraically? Component by component. x1 minus x2, y1 minus y2, z1 minus z2, right? Okay. So hidden inside this minus sign and inside this r is really, there are 3 components that are being subtracted. Okay. So that's what's going on in the numerator, and after I subtract these 2 vectors, what's sitting up in the numerator is another vector. Down in the basement, I'm dividing by a scalar delta t. Still a scalar, just sitting down there. How do I divide a vector by a scalar? By the components, right? So what this really means is delta t into the first coordinate, delta t into the second, delta t into the third. Okay, so secretly what's going on is secretly what's going on is that. And I'm using round braces, and I should be using angle braces. And the dot, dot, dot is for the z coordinate, which won't fit. Does everybody follow? Each one of these is a Calc 1 problem, right? Because x of t is really just a scalar function. And if you look at it, it looks exactly like the Calc 1 difference quotient. So the process is to differentiate R, simply differentiate the component. Now, there's not a hell of a lot of justification for going from here to here. Just because that's what worked in Calc 1 with scalars doesn't mean that that's a useful or reasonable thing to do in Calc 3 with vector functions. So let me try to motivate this geometrically. Why is this interesting? So why is this the right way to differentiate R? Well, let me try to explain that. Here's a space curve R of t. And I'm going to sketch in a vector a position vector R of t. And then I'm going to sketch in another position vector, R of t plus delta t. The idea is the particle is kind of cruising along the curve in this direction with increasing time. So if I take t and I add delta t, what I've done, and again, I'm assuming delta t is positive. It doesn't have to be positive. There's an analogous picture if delta t is negative. So I'm going to assume delta t is positive, which moves me a little bit further down the trajectory. So my position was at R of t, now it's R of t plus delta t. Is everybody okay with that picture? So this is the little dot moving along the curve. Look at the numerator here. R of t plus delta t minus R. As a vector, what is its direction? Or where is it as a vector in this picture? And probably, since vectors don't have location, I'll go back to my previous question. What's its direction? This is a displacement vector, right? And it represents the displacement direction from where to where? It represents the displacement from the beginning here, R of t, down here to R of t plus delta t. Does everybody see that? Okay. Nothing more than vector subtraction and the geometry of vector subtraction. What happens as delta t goes to 0? Yeah, that vector sort of shrinks away to nothingness. This is where delta t plays an important role. So as it's left to its own devices, this picture is not very interesting as delta t goes to 0. As delta t goes to 0, this vector turns into this vector, and that vector goes away. What I'd like to do is prevent that vector from going away. So what I want to do is keep the magnitude of that vector from going down to 0. One way to do that is to divide it by a scalar that's getting small. That's where the delta t comes in. So as delta t goes to 0, these two guys are coming together and going away. But with the delta t in the bottom, that prevents it from disappearing. It sort of actually means something. It gives us something useful. Why is delta t the right thing down there? So I've kind of motivated why r of t plus delta t minus r of t is the right thing, or a useful thing to think about here, because it's telling us the displacement as we go from t to t plus delta t. Let me try to motivate why we should divide that by delta t. If I were interested in the average speed as I went from here to here, what would I do? I would take the distance that I traveled and divide it by the time that it took me to travel, right? What is the distance that I traveled to get from here to here? The magnitude of the difference, right? And what's the time that it took me to go? Delta t. And so what this measures is sort of the average speed of the particle as it went from here to here. Agreed? So dividing by delta t and then letting delta t go to 0, well, what do you think that does? Gives us the instantaneous speed at t. And that's a lot like calculus. That was something, the instantaneous speed was something that you didn't really know how to do before you took Calc 1. That was kind of the whole point of Calc 1, really, was we knew how to do average speed, right? If I drive from here to Portland in 4 hours, what was my average speed? Well, I take whatever it is, 260 miles divided by 4 hours, and I get my speed, right? Miles per hour. Okay. Along the way, I could look down at the speedometer and get my instantaneous speed. But before we took Calc 1, we really didn't know what was going on and where that number was coming from. Turns out that number's coming from the derivative, right? The derivative is special. It lets us compute the speed at a moment in time, which is weird because there's no time at a moment of time. There's no time interval there. That's what's unique and interesting about calculus. We lift the same idea up here into Calc 3 and we get this geometric picture. So letting delta t go to 0 gives us the instantaneous speed at time t, and I'll sketch in what happens as we take the limit. What we get here, this is r prime of t. R prime of t is the tangent direction of r of t at time t, and the magnitude is the speed. So there are two quantities now. There's the direction of tangency, or the instantaneous direction is probably a good way to think about it. At this moment in time on this curve, what's the direction that I'm headed? That's the r prime. And then the magnitude of r prime is how fast I'm going at that instant in time. Remember, vectors have direction and magnitude. And so that's all mixed up in this picture now. Any questions about this picture? Okay. Let's talk a little bit more about mechanics, and then I'll move on. Let's pretend that we have a vector equation, r of t and t is just any real number. R prime of t. How did I say that we should calculate r prime? Component by component. So r prime of t looks like that. What is the significance of that vector? Well, if I pick up a value t, for example, at t equals pi over 4, the tangent direction to r of pi over 4 is negative root 2, and 1. And the speed is simply the magnitude of that vector. So it's the square root of 2 plus 1, root 5, whatever that means. So if I'm traveling along this helix and I stop at pi over 4, at that instant in time, I'm headed in this direction, and my speed is root 5, whatever that means. Okay, let's see a picture of that. So I'm going to switch back over to laptop mode. And let me get my helix. Okay. So here's a little dot traveling along this helical arc. Let me turn on the animation. Can you see the little red dot there moving along? Okay. So it's flying around in space along this blue path. And the black arrows are the tangent directions. And how do you calculate those tangent directions? You just take the derivative of the r function. Can everybody read that? I can blow that up. Control 1, maybe? Nope, that didn't help. There we go. Okay, and if I spin this around a little bit, you get different perspectives on it, and I can also, what can I do? I was going to put axes on this thing. Do I not get to put axes on this? Apparently not. Nope. Oh well. So you get the idea here. This might be like around pi over 4 right here. It would help if I had coordinate axes in there, but I don't. And that direction is indicated by this vector. The plotting software that I'm using here is the black tangent vectors are actually unit vectors. What does unit vector mean? They're length 1. So they're not indicative of the speed of this thing. They're just indicative of the direction. We'll talk more about the speed in a bit. Something that, just a bit of a look ahead while I have this here. Something else that we'll look at is the so-called principal normal vector. And not only is there this tangent vector at all these places along the curve, but there's also this normal vector at all these places along the curve. And we'll talk a little bit about that. This normal vector, whereas the tangent vector talks a lot about the velocity of the particle as it goes along the curve, what do you think this normal vector is going to tell us? It's going to tell us about the acceleration of the particle as it goes around. And then there's actually yet a third vector, which we will only mention and not really work with. There's this thing called the binormal vector, which is the cross product of the tangent and the normal vectors. And what that gives you is a little coordinate system, a little tiny coordinate system at every point on the curve that carries geometric significance. So at every point in the curve, there's this little natural coordinate system that's formed by the tangent vector, the principal normal vector, and the binormal vector. It's called a Frenet frame, and it's important in differential geometry. It's important in general relativity, that kind of stuff. Okay, so that was for cultural purposes. Moving right along. Actually, let me stop that so that's not slowing down the computer. Let's talk about how the derivative interacts with some of the other things that we've learned in Chapter 12. And so I'm gonna, rather than write this theorem on the board or on my notes, I'm just going to show it to you, and we'll talk a little bit about it. There we go. Theorem 13.7. So here in this theorem, it has lots of parts. We're assuming that R and S are vector functions, and that F is a scalar function, and A is a constant, some scalar. I mentioned this in the other class, and there were sort of a lot of O's. Wow, I didn't know that. So let me point something out. In this book, if something is boldface, like the R and the S, it's a vector. And if it's not boldface, like the F here, or the A, it's a scalar. Okay, so that might be something, when you're reading, it'll help you get things in context. And that's a pretty common typographical technique in math books. If it's a vector, it's often boldface. If it's scalar, it's not. Okay, let's look at these differentiation rules. The first one is akin to one that you learned in Calc 1. And really it just says that the constants don't affect the differentiation. They can pass through the differentiation. Right? So the derivative of a constant times a vector is just the constant times the derivative of the vector. That's great. The second one's similar. That's called linearity. So differentiation distributes across addition. And the same is true for vector-valued functions. And just without giving me a proof, in words, can you give me an intuitive feeling for why this might be true or why this might be true? Right? How do you differentiate a vector-valued function? What are the mechanics?
Each of the components.
Each of the components. And once you're in there on each of the components, you're back in Calc 1, right? So what's really happening here is you're adding these two guys together. How do you add them together? Component by component. How do you differentiate them? Component by component. Okay. And then once you're inside the components, you're in Calc 1, and differentiation distributes across addition. Okay, C is the first, perhaps slightly interesting one. C is the derivative of a scalar function times a vector function. First of all, how do you do a scalar function times a vector function? Algebraically, how do you actually execute that calculation?
Multiply, or within each component of the vector, you can multiply the function that's part of the vector and scalar function.
Right, so in the end, it would look like f times x comma f times y comma f times z, right? Then the derivative comes along and hits each one of those guys, right? Each one of those guys is a regular old Calc 1 product rule. Fx prime plus f prime x. Fy prime plus f prime y. Fz prime plus f prime z, right? And you're probably not surprised to learn that I can then split it back up and make it look like that. And that's really nice, because what it means is the product rule that I'm comfortable with from Calc 1 actually extends to scalar multiplication. Even more interesting is D. It says that the derivative of a dot product also follows the product rule. And that's fairly remarkable. Not nearly as remarkable as E, in my opinion, but still pretty interesting. Okay, let's talk about D. R dotted with S, scalar or vector?
It comes out of scalar.
Scalar. Derivative of a scalar is a scalar. So the right-hand side of this thing better be a scalar. Is it? Well, R prime, scalar or vector? Vector, S is a vector, R is a vector, S prime is a vector. Vector dot vector?
Scalar.
Plus scalar. Okay, so the dimensions work. That's a good thing. E, really remarkable given how hideous the cross product is, that the product rule somehow passes through this thing and survives the cross product. Really interesting. On the left-hand side, R cross S, vector or scalar? Vector. Derivative of a vector is a vector, so the right-hand side better be a vector. Is it? Yeah. Okay, good. The last one, what is that? That's the chain rule for vectors. Right, the derivative of R of f of t is just R prime of f times f prime, the derivative of the inside. Okay? So all of these rules that we're comfortable with from Calc 1 have analogs in Calc 3. And I'd like to say go memorize these, but in fact you won't need to memorize them because you'll just internalize them as you work with them. But please do, in the early going, remember that they're there. Stuff like this can save you a lot of work. What you don't want to do is start, you've got two vector functions, you don't want to drill down and start taking the dot product and then differentiating the coordinates, yada, 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 if you can avoid that. If you can avoid coordinates, do so. And these kinds of formulas let you avoid using coordinates. Questions about this theorem? My hope is that even though we didn't do a formal proof, that everybody has an idea of how and why these results hold. All right, let's keep going then. Yeah, we got plenty of time. Let's do some examples here. Let's go back to the notebook. Okay, and this is a problem that's not really in the book, but it's pulls together some ideas that you'll need anyway. Here's an example. I want you to find, or I want us to find, a parametric equation for the line that is tangent to the curve R of t, 2, let's see here, 2 cosine t, 2 sine t, and t at the point pi over 4, t equals pi over 4. Find a parametric equation for the line that is tangent to the curve r of t at t equals pi over 4. What kind of curve is this? It's a helix, and the radius of the helix is 2, and it's centered or swirling around the z-axis. All right. I'll try to sketch it for you a little bit here. Okay, and what we're really interested in is kind of a tangent. A tangent line right here like that. Alright, so this guy's sort of going up the helix like that. And we want the equation of the tangent line. This is all in 3 dimensions now. Alright, let's see if we can do it. What do you need to build the equation of a line in Calc 3? Nick? We need a point and a direction. So to build a line, and a direction. A point on the line and a direction. Point on the line. How do I get that? I can plug pi over 4 into r of t, which we can consider as a position function. And I get root 2 pi over 4. Good. A little bit dicier. How do I get the direction of this line, this tangent line? Nick?
You plug in pi over 4 to the derivative.
So I find the derivative, which gives me the direction of tangent lines all over the curve, and then I pick that one particular spot. Okay, I've got a point on the line and a direction. Right? Now what? Yeah, it's actually easier than like the equation of the line through 2 points. I just go straight here. L of s is, say, the point, root 2 pi over 4 plus s times negative root 2, 1. And that's the equation of the tangent line. Okay? I think I have enough time. I didn't do this in the other class, but I think I have enough time here. Let me see if I can get that thing into the picture on Maple without too much fuss. Just so you believe me. So let me switch back to the other display mode. right, and I'll see if I remember that. So I conveniently, and not by accident, have that exact helix right there. Let me try to build the line equation. Oops. In fact, why don't I just, why don't I just copy all this stuff, because I don't need the animation for this. And start down here. Okay, and then let's do okay, that looks good. And let me turn off all this stuff. Alright, nice simple helix there. And I can actually even turn on the axes now that it's not an animation. Good. Okay, and let's just look at where this thing's gonna be. If I sort of look down from above in the XY plane, I think that we're gonna be looking at a line right along here. But let's try it. So let me build that other parameterization. So, whoops. L is the function that goes to, oh boy, square root of 2, square root of 2, pi over 4, plus t times negative square root of 2, square root of 2, and 1. And let's get me R2 equals bless you. And let's call that L. Really? You're not going to type for me anymore? There we go. Okay, and let's get the line. Oh, let's just see what that does. Ooh, that was not helpful. Principal normal vector is always 0. I don't care. All right. I have a backup plan. Looks like the network decided to die. And this thing needs the network to run, sadly. So, I thought I had time. Apparently I don't. Alright. I'll get that for you next time. Let's move on and do a couple of interesting problems from the... oh, no, actually not quite. Let me talk a little bit about integration, and then we'll do some interesting problems at the end. So you'll not be surprised to learn that integrating vector functions is much like differentiating vector functions. You do it one coordinate at a time. And I'm going to talk briefly about a paradigm that you learned back in Calc 1, and that is the relationship between position, velocity, and acceleration. How did you go from position to velocity in Calc 1. Do you remember? And then to get to acceleration, again. Okay. On the other hand, if you flip that around, and if I handed you an acceleration function, you could find the velocity function, right, by doing what? Integrating. But when you integrated, you introduced this undetermined constant of integration, right? Do you remember how you got rid of those constants? Yeah, I had to give you more information. I had to give you an initial velocity, right? I have to give you an acceleration and an initial velocity and an initial position if you were going to move up that ladder. Remember that? Okay, that paradigm is actually still in place here with vectors. You'll not be surprised to learn. So let's talk very briefly about that. We have r of t can be thought of as a position vector. Then v of t, which is the derivative of r of t, is the velocity vector. And the magnitude of v of t is the speed. We're not going to talk about a yet. We'll talk about a in the next one. Let's suppose I want to go from, suppose I'm given v of t and an initial position and I want to find r of t. It works the way that you would hope. R of t is equal to the initial position r0 plus the integral from 0 to t v of u du. And what does that integral v of u du look like? You've got the initial position, you've got this vector of essentially 3 integrals. And what this does is it turns a Calc 3 problem into 3 Calc 3 Calc 2 problems. So, and that's you're going to see that a lot this semester. You take the Calc 3 problem and you turn it into a whole bunch of Calc 1 problems. Okay, which you all know how to do and you can do in your sleep now, and so this is not a big deal, right? Okay. This u here, and this u here, and this u here, don't worry too much about that. That's a dummy variable of integration. I didn't want to use v of t here because I have a t up here in its bad form in calculus to have a limit of integration with a variable that's the same, that's in your integrand. So what we do is we change the dummy variable away from t. We call it u in this case, or s, or whatever you want to call it. Okay, that's just calculus etiquette. All right, so there are a couple problems like that. Let's talk about some problems in the book here. So the first problem I thought was interesting was your star problem. Big surprise, right? Find the cosine of the angle between the curves blah and blah where they intersect. So this is one of the problems that you have to work on and have to give to me on Monday. A lot of steps here and relies on some stuff that you learned in chapter 12. Read it over and see if you have at least an outline of a plan for how you might attack this problem.
We're looking at 6 or 7.
7, I'm sorry. Did I say 6? 7. I didn't say anything. Let me draw a picture for you. Has everybody finished reading? Two curves. Here's a point of intersection. You got a plan yet? I want the angle where they intersect. Go ahead.
You could find vectors at the intersection of the two curves.
Any old vector?
The normal vector. at the intersection?
Actually, you could find the normal vector, but we don't have the tools to find the normal vector yet. But you could find the tangent vector. Okay.
And then use some of the dot product things we've done between those two vectors to find the angle between them.
Oops. Okay. That sounds like a good plan. How do I get my hands on the red vector? Derivative of R1 at the point of intersection. So there's still a little bit to be done here. Similarly with the blue vector, derivative of R2 at the point of intersection. Let's pretend that I have those two vectors. How do I get that angle? Dot product cosine identity, right? Dot product cosine identity. All right, good. So I think we have a plan, at least from that point on. Intersection. How do you figure out where they intersect? Yeah, kind of, sure. Where the coordinates are all equal, right? So let's look at the x-coordinates. Any information there? Yeah, so all points are going to work there. So the x-coordinate's not going to be a problem for us. The y-coordinate. And to be honest, I might look at the z-coordinate first. Are there any places where sine of t is equal to sine of 2t? Nick?
T equals 0.
T equals 0. Any other places? Pi? 2 pi. In general? Any integer multiple of pi. Okay, so the first coordinate is always equal. The third coordinate is only equal at integer multiples of pi. So now you're stuck with what? Integer multiples of pi. Which integer multiples of pi make the middle guys match? Well, I'll leave that to you to figure out. But once you figure that out, you've got your t that gives the intersection, and everything else flows from that. Right? Okay. Really quickly in the remaining 30 seconds, let's talk about one more. 12. A particle moves so that its position is given by blah. Find the maximum and minimum speeds of the particle. You have to be careful with the vocabulary here. This is a bit of a vocabulary test. So speed is the magnitude of the derivative of r. Okay, so that's the speed. Now I want to find the maximum and minimum speeds. How do I do that? Sorry?
You have to derive the velocity. Parametric equation you get.
Not the velocity equation.
You derive position to get the velocity.
So I take the derivative of position to get velocity.
And then you
Then I take the magnitude of that to get the speed. Now what?
find where it's less.
Now I do calculus on that. I do calc 1 on that to find the maximum and minimum of that guy. How do I do that? Take the derivative of that, set it equal to 0, find the critical points, yada, yada, yada. Okay? So somewhere in the middle of this problem, you're down 2 derivatives from where you started, right? But it's not just r prime and r double prime. It's r prime, then the magnitude of r prime, and then the derivative of the magnitude of r prime. Okay, have fun with that.